Okay, well, let me tell you a bit about my current lab. So, yeah, it's the Social Data Science Lab, as I started it in Austria. Actually, I started my first lab in the Complexity Science Hub with a very nice grant from the city of Vienna. And then I got my first tenure position in TU Graz, where I also grew up. But then it was a computer science department, and also my wife said I want to go back closer to Switzerland. And in the University of Constance, they have a very interdisciplinary political science department with an interdisciplinary master's program in social and economic data science. And so I was very happy to also move to Constance and try to build a bridge between the computing and the social sciences from the hardest part, that is the social science part, because that is where I am, the foreigner kind of person. So right now my lab is very interdisciplinary. So for example, I have physicists like Giordano De Marzo, computer scientists like Sebon Nagoyekun, and political scientists like Taiki Kim, or like psychologists like Alina Hederich and Hannah Metzler. So I really try to combine people from different disciplines, because I know I don't know everything, but it's possible to find the people who know that stuff. And in general, most of our papers combine several people in the lab to try to do more than just what we will do alone in our business. The biggest topics we work on right now are on studying emotions with digital traces and computational models, so like the subset of computational social science about emotions. And then on topics of information disorder, things like privacy issues, but also misinformation and manipulation online. And this is something, as I usually say, it's not something I chose myself to do or to go into as a research line, but in the last 5 years, the only grants I got funded are the ones that mention misinformation, and the other grants that didn't get funded is the one that did not mention misinformation, so it became a topic. And over time, I noticed the value of it. So there's actually a set of problems in society that misinformation or information disorders in general are symptoms of deeper problems. Some of those problems point to polarization and inequality that are also more long-term topics in my research lab, and especially in terms of affective polarization, linking back to affective science, like how sometimes people don't really disagree on what they think or believe, but they just hate each other more than in other situations, and trying to measure that and give generative explanations for where that comes from. So what I'm telling you today started from my research on the analysis of digital traces, in particular to study collective emotions, because this goes back to my PhD. I wanted to be able to simulate collective emotions with an agent-based model, with basically a representation of people's behavior that will tell me, for example, the situations under which there is a collective emotion. A collective emotion being defined as in psychology, that is a large group of people share an emotional state at the same time. So sometimes you can see that in the digital traces, and that's the first example I have there. This is a study I made of the terrorist attacks in Paris in 2015, and how we would see a collective emotion about the terrorist attacks and how long it lasted, what effects it had on the people who were involved in it, and so on. The problem is that when you see that, you see the trace, but explaining it requires a more familiar exercise of theoretical building, of theory building. Often one of my frustrations with social science theory or psychological theory is that it's very verbose and not quantitative enough for me to be able to make predictions, to validate the theory. And an approach to that is making agent-based models that is basically a way to force you to write a code that represents your theory. Not theory in a normative sense, but theory in a natural science sense, that it explains the world, and if you're able to code it, then you are precise enough for it to be testable. Testable in the sense that you start from some microdynamical principles, like people affect each other with their emotions, or they influence each other, and how that generates a collective outcome, like a collective emotion, which social media data helps to validate those predictions. But that doesn't really tell us much about the behavior of individuals. Usually the behavior of individuals have some causal statements that say this thing makes a other person behave that way. And social media data is notoriously hard to use for in high internal validity, in the sense of telling you what is causing what, especially at the individual level. So over my career, I tried several times with experiments and showing emotional content to people and asking them how they feel, also with physiological sensors and so on. And you can get some information, some features of people's behavior that way. But from an experiment, it's very hard to interpolate, not extrapolate, but interpolate to slightly different situations that are kind of in between your experimental setups. So sometimes it's easy to find an effect, but hard to find a smoothing of people's behavior that you can put into these models. And so one thing I'm showing you today is part of my approach to try to calibrate this microdynamics, this behavior of people, so that we can put it in a bigger theory with other data sources that are not only experiments. And very goes into why am I talking about LLMs today, is because there's a growing work on social simulation with generative agents, where a generative agent is basically a software agent that can use an LLM to decide on its own actions in a simulated environment. And this became especially popular last year with this paper by Soyun Park and colleagues in the University lab in Stanford, where they just put a lot of LLMs to talk with each other in a simulated town, where they could do actions through text, and they can say like, I want to go to my friend's house, or I want to pick a flower from the garden, and it gets enacted, and other agents can see that action. It's all symbolic, of course, but at least they could show, hey, these agents are able to talk with each other, and they have some anecdotal observations, like they organize some Valentine's party, and other people join, and so on. So it was a proof of concept that you can put LLMs to interact with each other, and perhaps they can show behaviors that are not as trivial as just what you see when you analyze an agent alone. So by that point, I was a bit sick of LLM papers, I must say, and I was like, okay, now you do sentiment analysis again, but with ChatGPT, congratulations. But when this came, I must confess, I read the paper because of this figure, that it was like an 8-bit figure, and I really like 8-bit art. And I was like, oh, okay, let's take a look. And then I was like, all right, well, this sounds like a very new idea. What if we try to improve our agent-based models instead of only with experimental data? We also use the LLMs as a way to interpolate in different situations and to have a better representation of the behavior. Of course, it's not that simple to build an LLM that represents what we are missing in terms of the behavior of people, but it seemed like a promising way to fill the gaps that agent-based modeling was having. If you read the texts of people who were developing agent-based modeling in complexity science, like 20 years ago, they were saying things like, policy making will be based on agent-based models 20 years in the future. And it's not happening at all. If there's any science that has an actual effect in policy making, it's basically economics. And it's because it's a very good science into hiding its assumptions when talking to politicians. So they want to make those assumptions more explicit by being able to operate on them on the LLM. There was already some work on doing this last autumn by Victor and colleagues and Chris Bale, who were doing this on a situation I especially like, that is a social media platform where people interact mostly through text, as Twitter. And they were saying, let's have agents that are initialized with an identity based on a sample from the ANIS survey we use. Like, they will sample a person from the survey, give it as a persona to the agents, then populate the social media platform with the agents and implement an algorithm so that they interact with each other, so that you can make experiments and which, what if you change the algorithm and have, for example, you hide retweets or things like that, what comes out into the behavior of the agents when you're making that kind of in silico A/B testing. And this was also basically the way I was going to, like, we made some workshops together and so on. Can we tell something about what could be the effects of a policy or an algorithm change or an intervention by having an in silico simulator of people online as a way to inform better what are we going to do in the future with platforms? Because one of my struggles now is that, for example, the experiments that Facebook and Instagram did in the 2020 election were mostly motivated by a model-based discussion among academics, in which we were saying, hey, we think there's a problem with echo chambers and with filter bubbles. You have to remove like-minded content from the timeline, and this is going to solve polarization. We didn't have a proper simulator that said by how much is it going to decrease, or on which people. And that's why it was so unspecified that other problems with the experiment, of course, could be present, but even if the experiment was super powerful, the hypothesis was too naive, and we have to be a bit more precise on what do you actually have to do to influence an outcome. When we're working on this direction too, we got a project funded recently from the Horizon program in the EU. It's called What If? And it's going in that direction too. This is with colleagues, for example, in the Netherlands and in Austria, in the UK. And what we're trying to do is that we're going to build on agent-based models and use LLMs to fill the theoretical gaps that we have in LLMs by developing on the theoretical gaps we have in agent-based models with the LLM, and by training and validating the LLM against data donations that we're going to get from several countries. So the idea is that, especially we're working with Annie Walker in Vienna, who's a communication scientist that has been using LLMs, agents for a number of years. And we want to be able to have basically an agent-based model that also speaks and generates an observable trace of each behavior so that it's comparable to what we can also see online. So the idea is that we want to have this what-if simulator where we can change things that are not the algorithm. We can simulate, for example, one thing we want to simulate is what if you triple the funding for public broadcasting? And then you are not fighting misinformation by trying to censor it, but you flood the social media with a lot of well-curated information or produced under some guarantees of journalism. Will that have an effect, for example, on misinformation sharing? Maybe it doesn't. Maybe the misinformation is so powerful that it doesn't. But there's a lot of other things that are not just algorithms we want to test. And so we have this 3-year project that starts in January on that line. The contribution of my lab is mostly on the interface between the LLM and the agent. How can we make a computational agents model that has words and doesn't just communicate through numbers of opinions? So I'm going to show you today 2 papers that we started working on that direction. It's still not exactly on interventions on algorithms and so on, but at least on how we're building simulations in which LLMs interact with each other and what we're learning from that. And one of them is that we wanted to see if we put these LLMs to talk with each other and they produce a social network, they start linking with each other, how plausible is that network? In the sense that we are training these as text agents, they don't really have a concept of the social environment or what is becoming a friend of someone. If we put 1 million of these to interact with each other, will they produce a network as what people do, or will have very different structures? Because many of the properties we know these networks are emergent. You only see them when you see millions of agents and not when you analyze only one. So we have made a boilerplate simulation in which we are having LLM agents that enter a social network, and we pose them with this question. We say you've entered a virtual social network. You are tasked with connecting to n individuals, so it's kind of simulating or reflecting what we also have in models of growth. When someone enters a social network, they connect to some people, and then we show them in different scenarios some information on the individuals. Sometimes we show them the number of friends they have, sometimes not. Sometimes you see this in platforms, sometimes you might not see it. And we wanted to see what are the structures of the network. In particular, there's a degree distribution that is the first thing you try. If a network model does not represent the distribution of number of followers or number of friends of people, it's not a good model. It's the first thing you need to represent. So we simulated this, and we have 2 conditions we could value, so the matrix of 4 options. One was showing the number of friends of the other agents, and sometimes not showing the number of friends. And another one, it was renaming and not renaming the friends. And I will get into a second why we were doing that. Because the most typical one you will do, it will be showing the names of friends and showing the number of followers. And when we did that, we got this kind of network here, which is called a hub and spoke network. It's ultra concentrated. Basically, some agents get all of their friendships, and the vast majority of agents don't have anyone following them, so to speak, no friendship resources. This is pretty unrealistic of an online social network. In general, we have more variance in the number of friends that people have. So this was something that we were kind of expecting. You tell the identity of people, you tell the degree, suddenly it comes to this range. We did an experiment and we removed the degree information. So we didn't tell the agents the number of friends of the people they could connect to, which, not having no information on the number of friends, we thought it would lead into a completely random network, and in which we wouldn't have any kind of hubs. And when we simulated that, we get what is called a power law distribution. So we have some high degree nodes and a lot of lower degree nodes. And we were really puzzled by this. Like, how is it possible that when we don't tell the number of friends to an agent that is connecting to the network, they still manage to construct this kind of inequality number of followers that we know it requires some information on the number of friends. And so we analyze this a bit more carefully, and this is why I'm showing here the age of nodes. And the orange nodes, the yellow ones are the older nodes. We know that in general, in network growth, older nodes get more friends than younger nodes. And this network was kind of violating that. What we discovered is that LLMs have a prior on how they construct or they create tokens. And what we see here, the distribution of this is not the degree distribution, is a Zipf's law on the language. And Zipf's law shows you that you have certain words that are very frequent, certain that are not. And you have the power law distribution of frequency of terms. So this structure happened because the large language models have learned already scaling distribution in language that is on token frequencies. So when you ask them become a friend of someone, it means saying the name of that person, saying yes, we're basically a random character string, but there's still Zipf's law on random character strings. So it's not the same as you click and become a friend of someone, you say, I want to become a friend of blah, and that created a bias in the production of this. So that's why we noticed it's not the same becoming a friend of someone as saying their name. So we designed a version of this in which basically people get renamed every step, so the reference is get there, but we simulate something that is more like clicking the becoming a friend of a person by just basically renaming things that they become IDs in the system. And when you do this kind of renaming, then you see what we were expecting. With the information, we get a typical, very pretty realistic network, or at least number of followers, as in an online social network. And we want to remove the degree information. It's a random network. This is on the linear scale where you don't have these hubs. So more than we learned two things. So first, that an LLM system can reproduce some of the features of the online social network, like the degree distribution, but you have to put yourself in the terms of the LLM, and if you are just asking to verbalize the actions, you will have biases of language. And here, Zipf's law was one that was producing something that looked complex, but when having a bit of the knowledge of complexity science, we noticed that it was a red herring because of that correlation we know from previous models that you need to also rename things. And we continue doing this. All of our studies, when you use the name of something, you are biasing the behavior of the agent by this prior of the tokens. Actually, we went more closely and looked at, for example, how robust was this over time, that you see like this kind of distribution for different sizes of the network. But also this particular distribution, this kind of scaling exponent, is a very particular one. This exponent of 2, which only happens when you have a preferential attachment, so meaning that nodes are more likely to connect to other nodes that have higher degree. So the probability of a node connecting to a node is proportional to its degree. But this 2 you get only when this is linear. So when there's the growth of the probability happens basically on a linear scale. And that's very particular. So I was expecting this to be some whatever function, who knows, but not linear is a very special case. Non-linear is a much more general case. And that's one of the values of an LLM, because we can simulate the agents in isolation and see what happens if we give them nodes of different degrees and see how they react to this simulated scenario that is not even in a real group simulation, just for the representative agent. And then you can have a much better understanding of the behavior of the agent because you are kind of taking it out of the simulation and put it in a test bed. And that's what we could see there, that there's a linear growth. Okay, there's a whole methodology how to do this. It looks like a quadratic cumulative function. And the node in isolation is much more likely to connect to a node with DK with a linear function of the degree of that node to connect. So in anything, it's not just about putting LLMs to talk with each other. You can also isolate one of these agents and try a lot of weird configurations to see how it behaves. And then to use what we know from statistical physics, complexity science, or math to make to understand what happens when you put a lot of elements together. And I think this is rather important because physicists and complexity scientists have been freaking out a little bit about LLMs because they see in general they don't like artificial intelligence. Right before ChatGPT came out, most of the physicists would tell me this is just overfitting. And now they started to take it seriously, and they're talking about the complexity science winter. That now, why do you need a model of the behavior of an agent when you can just have an LLM instead and simulate it with it? or with artificial intelligence that kind of interpolates better the behavior of whatever you're analyzing. And I'm telling them the opposite. It's like, no, the science is still meaningful. It's just not explaining everything as they were trying to tell us. The physicists that they can explain, they can tell us something on top of what LLMs do. They can tell us how the LLMs will combine and what can we predict of the behavior of the society of LLMs for complexity science. But they still have to talk more to them to calm them down because there's in general quite a rejection towards artificial intelligence just because it's not simplifying the explanations of things, but actually making more parameters rather than less. Okay, without getting sidetracked, we wrote the archive preprint on this. It's very short, but at least it's a first proof of concept that when you put a lot of agents together, they can still show what people do. You just need to be careful and not jump on a wing when you see a power law. Then you have to think carefully that it really represents the social network. So from this, we moved a bit further and we noticed, okay, now we're simulating society with LLMs, but what we noticed in the last few months is that society is starting to use LLMs in the society itself. There's this claim that, for example, Apple is partnering with OpenAI so that they claim that your phone is going to have an LLM running on the back and it's going to be doing things for you. I mean, it's not doing it yet, and we're selling the bit, but it's not impossible that you have iPhones talking with each other behind your back, basically trying to get stuff done for you. So, for example, in the morning you wake up and you say, like, I want a restaurant reservation in a fancy place. And then the LLM is going to be calling restaurants, and the LLMs of other restaurants are going to be replying, and they will find the reservation for you. You know? I'm not making this up. You know? Or do my taxes, and then you're going to be talking with different tax LLMs and try to find the one that makes you better. And this is only one, so now there's more. I mean, of course, everything has a lot of snake oil on top, but it's not impossible that, especially in some areas, we start having LLMs behaving as representations of people to do the things we don't want to do in terms of coordination. And this made me wonder, so what if we have layers of society that are already automated like this? We have precedents of this. For example, the stock market is a place where you barely have humans trading, and you have mostly algorithms and bots. When humans trade, they do it more in like a small platform like Robinhood or whatever, that usually not even visible in the real stock market. In the stock market itself, there are not humans anymore, and there were ugly surprises when machines were taking over. An example is flash crashes, or how all of the bots were synchronizing all of a sudden, sometimes without even a real explanation, and suddenly tanking the stock market because they listen to each other too much. So when you have people have some limitations, and sometimes those limitations are useful to prevent some crashes or unexpected results. Sometimes the limitations are a problem and they create issues, inefficiencies, and so on. So if we have these kind of LLMs, do we have things like systemic risks? Do we have things like more opportunities and higher value? What could be the problem, especially if these chatbots are coordinating each other? There are situations in which there's no objective best solution. It's just a norm situation when there's no real reason why they should be doing one thing or another. And thus, it's a very nice example to analyze when would they have or produce a risk, because there's many situations in life when there's no right answer. Usually the price of something doesn't have a right answer, whether it's too high or too low, it's just something normative. So could they have these kind of norms emerging in a situation in which there's no preference at all? And what is the scale at which this could happen? Because we know that for humans, there's a limitation on how these kind of arbitrary norms emerge. And this is linking to anthropology, and then you have like the social brain hypothesis that says that groups of animals, sufficiently intelligent animals, mostly mammals, but mostly primates, they need to have certain abilities to be able to identify each other and explain the behavior of each other to form groups that are stable. And so there's this finding from Robin Dunbar, for example, that he was looking at the scaling or the relationship between parts of the structure of the brain of animals and the size of groups they produce. And he discovered that there's the ratio of the neocortex to the rest of the brain. So that's like the surface that you have on the brain that allows you to identify the identity of other people, is correlated with the average size of a group that different species produce. Average size of the group as they are able to identify that someone belongs to the group when they see them or not, and then they change their behavior based on that. When it's part of the group, you can, for example, let your children close to that one, but they are not part of the group. And they can also coordinate, and they go to the left, they follow the group to the left, they ignore other groups. And the extrapolation from that is that he predicted that humans will have an average group size of about 150 or 200. This is commonly known as Sandler's number. But this is a definition of a group that is a very informal group that requires lots of unwritten norms that don't have an explicit norm. We have, of course, societies that are much 100 and 150 people, but they require explicit rules and institutions and decision processes to formalize those behaviors. When you're having a random group of people and they have to basically agree on their behavior, they tend to split into smaller groups. And then in those subgroups, then you have a more homogeneous behavior. So well, there's a number of evidence on how, when you're having that informal situation, group size is limited, and humans don't want to go beyond larger numbers, they would rather split. And I was wondering, where are LLMs here? So if we put them in a situation in which they have to decide on a very random rule, like in the stock market, they just buy or sell this completely arbitrary speculative thing, will they be able to coordinate on one of these arbitrary norms? And if they do, is there a limit on that? No? And especially does the limit depend on some sort of cognitive ability with the LLM? In particular, also Robin Dunbar says that actually humans in reality are a bit beyond what would be predicted by this. And one hypothesis is that this is because of language, being a tool that is actually able to create larger scale coordination beyond what just our brains are able to do. So even the anthropology literature is saying that this is not just the brain for identifying other people, it's actually being able to communicate with people, and it's the language abilities that predict the group size. So I wanted to do this with LLMs, with Giovanna de Marzo, my postdoc in Constance, and we set up an experiment in which we're simulating LLMs talking with each other on an arbitrary decision. So we just take a group of agents that just look, they see each other, they see everyone, and they look close to the side, so we can make pretty much as large as we can play. And we show to each agent the opinions of every other agent. And these are again arbitrary opinions, which start with something like X and Y. They will start with two opinions, but the agents can free write and say whatever opinion they want. Actually, that never happened. They stick to the opinion options they have. Of course, we didn't try to put a high temperature, but they still stick to visible opinions before. And every time, every turn, we show the agent the opinions of all of their agents, and then there's what is your opinion? And then we just take the opinion vector, and then we show it to another random agent, and say, see the opinions of all of them, what is your opinion? And these are, again, there's nothing objective into why whether one is better than the other. There's no actual real discussion, it's just communication through the display of that arbitrary option. And then we test whether the LLMs are able to coordinate on this, and they actually agree on some option, and whether this depends on their language abilities and the group size. First of all, when I started with these experiments, I thought, I don't want to use a lot of money for this, because I don't believe they will coordinate on anything, because there's no reason why they should. If we get anything, we're going to end up with the prior of the probabilities of the tokens, as we had in the other experiment. We're reshuffling them to try to remove that, but this time it will be like whatever original distribution we have, it will be more or less the same. But to my surprise, LLMs are able to coordinate in this situation and find a consensus on this completely arbitrary choice. Here I'm showing you just some examples with certain models for a group of 50 agents talking in this scenario. And here the time every update is an update of every agent. You know, like we have a time that is proportional to the size of the system. Some models are more or less I was predicting the cheaper models like GPT-3.5, Claude Haiku, Local Llama. They coordinate a little bit. I mean, this is the consensus level. So basically, in physics, it's called a magnetization. So it's something that measures whether all of the agents are in one choice or another, and then you take the absolute value of that. So it's between 0 and 1. And so 0 means that it's 50-50 divided, and 1 means that they all agree in whatever option they have. So these models kind of end up with some sort of slightly one group is maybe a little bit higher than the other, but it's pretty noisy around there. But if you take the more expensive models like Claude 3 Focus and GPT-4, they reach consensus. And actually, I think this is 5 simulations. They reach consensus in all 5 simulations in about 5 rounds of opinion. And this was, I mean, actually, when I saw this, I was like, okay, we don't need to work more, but your learning system, no, come on, it's cheap. And then is when we discovered everything. I was like, okay, now we have to start studying this. Luckily, we were not paying for GPT-4. We had some of the free credits that OpenAI was giving back in the day. Actually, I think for this, we have paid only to Anthropic, nothing to OpenAI. So then I thought, like, okay, let's try to study this. And what we did first is that we isolated the representative agent, as we did for the network. And we can show now to this agent not a really simulated vector of opinions, but we can manipulate it and have a higher fraction of opinions on one side versus the other. So now we're isolating the agents, it's not a real system. And we can show them different situations with different collective opinions, like everybody agrees on the first option, everybody agrees on the second option, here is 50-50. And now we can see the probability that the agent chooses the first option. So this is the typical sigmoid function. This in marketing is called the S-curve. Usually it's like out of how many of your friends have chosen one, for example, phone network company, what is the chances that you switch to that network company. So if you will like 0% of your friends have that network company, usually it's 0. And then there's some cutoff somewhere, there is 50%, but it could be elsewhere. And then there's a point in which if all of your friends have switched to the other phone company, then you will switch. So we tried with different models, now we expanded the list. And we see this kind of sigmoid function. Some models, like you see here, Claude 3 High, with a very cheap one, so typically 3.5. They have like a very flat, very noisy, but still relatively flat shape, so they don't listen a lot to the majority, to the rest of the group. Some models listen to some extent, like they still have some base probabilities of disagreement, so to speak, but they still, they're above the 0.5 line and below. So these are things like Llama 3, that already looked like it was coordinating a little bit before from Claude 2. And then the most expensive models have, and this is for 50 agents, they have a much more light curve, and we think that there's more of a force of the majority for them to comply with it, so that if you just change the majority a little bit from 50%, then you jump towards the majority. And so we call the discounting model with one parameter, is basically a tangent with a beta. And we call that the majority force that tells us how curved this is and how much. If it's a complete step function and beta is infinite, and it will always switch. But when beta goes down, it basically starts being shorter and so. This plot here is this type of plots that physicists love, that you rescale what's happening by beta, and then you see that the plot looks like one line, so that they collapse the behavior when you normalize by beta. In social science terminology, this means that the residual distribution of both models, of all models, is the same. Just translating in case you think in terms of statistics. So now we have this beta that we can measure for an LLM and a number of agents that we simulate. And we can, first of all, we look at one size here. I think it has 50 agents. And then we see how the majority force that we can measure depends on this NMLU benchmark, that is linguistic ability of the agents, as Lampard will predict, saying like there's basically more ability to coordinate in a group when they're able to understand each other. So first in this one, we found that there's some correlation between this majority force we measure for a particular size and the language understanding of the model. So that models with higher language understanding, they have a stronger majority force. And we tried with other things because I thought this could be just the context size of the model that is able to remember bigger groups, but we tried with context size, and actually it's not that correlated. It's not significant with the sample that we have. You see the correlation is much weaker. So it's not just about context size. Context size is a component of language understanding that helps to explain this coordination ability. But going towards what Tamar was saying, Tamar wasn't talking about the force itself, but about the group size. And so we started simulating for different group sizes. I mean, I was showing you here with 50 agents, but we tried with less agents and with more. And we started to notice that the majority force that we could observe was increasing with the size of the group, that the tendency to comply to the group size weakens with larger groups. And in particular, there's this cutoff here at 1, where we know from statistical physics that below 1, basically consensus is impossible. Or if it happens, it's just by chance, because there's some probability that agents just flip here and there, and then by chance they could agree in consensus. So basically you have to wait the exponentially increasing amount of time to see some consensus. And above 1, this consensus is possible. Doesn't mean it's easy, but it can happen. So we see that for agents with increasing sizes, some of them cross this line, and this tells us that probably the critical group size at which consensus can exist for an LLM is somewhere here where we can see this kind of cutoff. So we went one step further, and now we apply statistical physics. And this is just a warning because when I was in Vienna, physicists love to use Ising models to model everything. So that's a model of a magnet where atoms are representing like up and down spins, and they say this is like an opinion, you disagree, and then they model everything with an Ising model. Especially during the pandemic, they were doing everything with an Ising model and saying that you can explain, for example, the effect of the intervention with an Ising model when people are infected or non-infected. That doesn't work very well, and that was part of my frustration during can you use an actually mixed model and not another Ising model. But here, my words came back to me because an Ising model was actually useful in this one case. And because when we're looking at what the agents are doing, we can say this group of agents that are all coupled with each other is like a magnet, actually. They're like atoms that are connected to each other and coupled with each other in a big object. And when they agree or disagree is when the object gets magnetized. So something becomes magnetic when all of the spins are pointing in the same direction. So actually, statistical physics tells us how the size or the number of particles in that system and the temperature of the system is telling us about the probability that it's magnetic or not. So actually, everything has some probability of being magnetized, just extremely low, because they're very large particles and we're at a very high temperature. But if you reduce the temperature enough and if it's small enough, it can become magnetized. And so this is what happens here. When there's consensus, is because this thing has become magnetized. And the majority force, the beta is like the temperature, and a group that an agent, an LLM that has a very high majority force is at a low temperature, is able to coordinate faster, is able to stay in a coupling system, and the size is making it harder for it to magnetize. So actually, in physics, we have what is called a Curie-Weiss model that is telling you when you have one of these magnets, what is the time it takes basically to magnetize as a function of the size or the number of atoms, the temperature. And here I show you an example. These are some, here first of all, we have the GPT-4 Turbo that is still in the consensus situation, it still creates consensus for different group sizes after a certain time. And we can measure the beta coefficient, the majority force for each of them, and this Curie-Weiss model is agreeing very, very well with GPT-4. Also, a cool thing of this model is that it tells you there's a point in which basically the beta is too weak, and then you are having an increasing time to reach consensus because it becomes by chance, it becomes random, and at the point it just goes ultra fast. It goes with an exponential function of group size. And we see that in other models. For GPT-4, we see it when it starts to grow. We don't do it anymore because when you're simulating several hundreds of agents for many, many steps, it becomes very expensive, but we see that it starts to grow. With Llama 3, we also see when it starts to grow. So kind of these points here, when we're using that analog of a magnet, allows us to tell under which size we cross from this kind of linear phase to this exponential phase, and that tells us what is the critical group size, after which an LLM is embodying these agents is not able to reach consensus. So that allows us to measure this Dunbar's thing, so there's a critical group size, after which you don't have that spontaneous coordination anymore for every agent. And now when we compare with this NLU benchmark, this language understanding of models, we get quite a function relating them, the typical exponentially increasing group size with language abilities. Humans are on this line too, so because humans have a benchmark value, they have a language understanding ability and a group size of what we know from anthropology. But when we did this, we saw like, okay, these models agree, but there's some that disagree with this line. And actually, when we went to like GPT-4 and 3.5, we couldn't break the model in the sense that when we already simulate like 1,000 agents, it gets very expensive, and they still manage to reach consensus. So we stopped there. We didn't look for the point where they will not reach consensus anymore. But we saw that for the language abilities, this is already basically an order of magnitude larger than what people do. So in my concern of like, would there be some emergent behavior on a society using LLMs that we don't see with people? It could happen, at least in this very boilerplate conceptual exercise, that they can synchronize at a scale that is larger than humans in something that is completely arbitrary. And again, if humans are able to coordinate, if you think about the stock market, maybe 150 traders manage to coordinate with each other, but they don't manage to sway the market. That's why it doesn't collapse that easily. But if instead of having 150 humans, you have all of these agents, and there are millions of them, they could end up synchronizing and having some ugly surprises. So now there's discussions about, like, for example, Cesar Iago has a very interesting idea. What if we have, instead of a human representing you in parliament, you have an LLM that represents you, and you talk to the LLM on what are your ideas, and then instead of having 300 people in parliament, you have as many as the population. In my parliament with like 50 million people, and then they all discuss with each other and they come with a perfect solution that satisfies everyone in the society. And so first, with this, there could be surprises and some agreement among agents that we didn't expect, because yes, there's not a situation in which millions of humans really coordinate and interact with each other. That's one thing. And second, my fear is that that solution is something that is completely intractable to humans. Like if already the laws that humans produce in a normal parliament are impossible to read, imagine when they're made by chatbots. And then instead of 40 pages for a law, you have like 40 million pages of the law. And then only other computational agents are able to enact the law. You need to also have LLM-based policemen, you have LLM-based judges, and then you start by trying to do something nice and making part of the society more transparent and end up in dystopian future. So it makes me think like that. No? You never know what's going to happen with a system like this. That's why you need like another kind of AI complexity science that is, I would say, easier actually than human complexity science, because with humans we cannot really experiment with them that much. But with these LLM agents, we can put them in a test bed and have a better explanation of what they do. So just okay, summarizing, we have this idea of first, we can have perhaps models of society that are improved or more realistic thanks to having LLMs. And that's what we see with the growth of the network, that it shows some behaviors that we see in humans too, and that are not really for granted in the design of the LLMs. And then when we're starting to have a society in which we're running LLMs in the background, so to speak, I start to worry like what happens when there's emergent behaviors on these large groups of agents. I just started from a very simple situation of like what if they coordinate on something, and I found that depending on the linguistic abilities of the model, they are able to coordinate at larger or smaller sizes, going beyond what we see from humans. That was kind of one of our concerns. So now I'm going to try to do social simulation with large language models, kind of building on the first part, but now I know that they have to put a limit on with how many agents can one agent interact. Because if we let them talk to anyone, they might create this kind of soup of ultra interaction between them, and then not be realistic anymore. So you cannot have put restraints on your models and to make them realistic. If you want to learn more about this, we have the two preprints, and there's more papers on this in my website, the Garcia.eu, and I just made a Blue Sky account with my domain, so you can also follow me there. I'm barely post on Twitter anymore, so the cool stuff is in the archive. Well, thanks for your time. Looking forward to it.